Hi, today I'm going to take you through a brief tutorial of Quantum Composer. You can see that I've got Composer open in this window, and the interface looks like the following. Up here you've got the typical menu options, and here on the side you've got a bunch of different node options that are grouped in terms of what types of operations they deal with. And as I take you through a sample exercise, hopefully you'll get a better idea of what these different nodes can do. With this tutorial, I'm only going to take you through a few of these nodes, and I'm hoping that the reference and any of the exercises can help you in understanding some of the nodes that I don't cover here today. So what I'm going to start with is just by setting up a simple system that's time independent, and I will show you how you can change the potential and how you can get the energies and the eigenvalues and the eigenstates. So let's start. First we have to define space. So we drag out a spatial dimension node, which is here. And you see that it's got a spatial dimension output here that's colored yellow. And you can set the limits of your spatial dimension. So let's go from -5 to 5 just for fun. And then this n is basically the number of steps. This sets your spatial resolution. And it's best if n is a power of 2 to the n. I typically like to set it around 512. That might be overkill for some of the applications that I'm going to show you here today. But you can always play around with it, and it's always best to test the system as much as you can to make sure that you're getting accurate results. So, what do we do with the spatial dimension? Well, we can define a potential. And you see as I drag out this potential node, you see that the potential that we want is written here in this text box. It defaults to the harmonic oscillator potential with a trap frequency here of A. And you see that it wants as an input, inputs are on the left, outputs are on the right. It wants as an input a spatial dimension, so we can hook that up. And you see that when I hook that up, a missing input, this error here goes from being just an error to a warning. And the whole idea is that the potential input will not work if you don't define a spatial input. But it would work if I didn't put in any other inputs. Except now it sets A here to 0, which is going to set this whole entire potential to 0. So how do we work around that? We need to define a trap frequency. So here I go down to the scalars here, into scalar input. I can drag this guy out and wire up. And you see now that my warning is gone, but of course I've kept A at 0, and that's going to have a very uninteresting potential. So let's set A to something, say maybe 2. That's a reasonable start. And you see here that we have an output, this blue output here, and that defines our potential. Now what can we do with the potential? Well, we can define a Hamiltonian. And so the Hamiltonian, being the sum of the kinetic energy plus the potential energy, already has the kinetic energy term in there for a one-dimensional single particle system. And we can wire up the potential, and you see that the error here has gone away. So that's great. But what can we visualize here? Composer really comes into its own as a visualization tool. Well, I can drag out one of these energy plots. And you see that the energy plot here has as inputs a potential, a Hamiltonian, and then a state here, psi. This will work with any of these hooked up. And so as you can see, I can wire up the potential node. And you see that nothing's happening, but that's because I haven't shown the potential on the screen. And so I can click this, and you see now that the potential shows up on the plot. Let's change this to 1, and you see that we're working very nicely with this harmonic oscillator potential. One thing that you need to understand is that in a static case, these walls here are going to be hard boundaries. And so, for example, if I were to set this to 0, Composer would see this actually as an infinite potential from -5 to 5. And so it will give you results corresponding to an infinite potential from -5 to 5. If I, for example, increased my maximum y up here to, say, 20, you see that above about y equals 12.5, we've now hit the boundary. So what Composer sees this as is a harmonic potential with infinite walls at the boundaries. Okay, these are little details, but they might be important when you're trying to debug your simulation. So let's go back down to, say, y equals 10, and let's try to click here on these energies and the eigenstates, but we see that nothing shows up. And the reason is because we have to wire up a Hamiltonian to it. And so now that we've wired up the Hamiltonian, now this plot can show the energy eigenvalues and the eigenstates. Here with this box, we say that n eigenstates is 1, and I can change this, for example, to 3, and it will show the first 3 eigenstates of the potential as well as the real part of the wave functions. And you see that, as they should be, the harmonic oscillator energy levels are equally spaced. And things will change. If I change A, you see that if I make it smaller, the energies become closer together. If I make it larger, the energies move farther apart. And the eigenstates look as they should, an increasing number of nodes as I increase the number of eigenstates, and so on and so forth. So this is pretty cool. I can do other interesting things. For example, I can set up a basically a box potential. So I could say minus box from -a to a, and this should give me a box potential that is attractive. And so we'll go from -10 to 10, and you see that I have a nice little box here. I can say, but I want to make my box deeper, so I can multiply it by a b, and you see now that we've thrown an error because the potential doesn't know what b is. So I can actually define this. I can say, yes, this is my b, and I can wire it up to this plus, and you see that a new variable named b pops up. And I can set b to be 10, and now I have a finite well potential, as you can see. I can change ymin and ymax so that it's much easier to see what's going on, and you see now that the energy levels are no longer increasing they're no longer equally spaced, but you can see again that we have multiple nodes as we go up in energy, and we can plot as many of these as we want. And so this is a really nice way to visualize different potentials. For what continues, I'll actually go back to the harmonic oscillator potential. So we'll go back to 0.5 times a squared times x squared. Okay. And we have to reset our view, which I can do just by going ymin to 0 and ymax to 10. Alright, so now we see our harmonic potential again, as we see. This b potential, this b variable here, is no longer needed, it's no longer used. Having it there isn't going to cause any problems, but it can be confusing, so we will just remove it here. Okay, so that's the most simple thing that one can set up in Composer. But what I want to show you is how you can actually get the spectrum of the system. And that's done with the spectrum node that's under linear algebra. I can pull this out here. I can hook up the Hamiltonian to it. And I have a similar number of eigenstates. And the outputs are a list of the wave functions and a list of the energies. Let's say that I want to show some energies. So I can pull out this get eigenvalue node, as I've done here. I can hook it up, and the energy states are 0 indexed. So we see that the 0th energy here is shown below. It's actually 1, which is really nice. The first excited state is at 3, which is what we expect. You see that this corresponds to the different levels on this plot. The second eigenstate, oh no, we can't see it. It's not in the list. And that's because I have to increase the number of eigenstates here. So you see, now it shows up as 5, as it should. We can use this output if we want to for something. We can also set up a scalar output, which is actually redundant right now with the number that's shown below. And it's just an option if you want to, for example, make it easier for students to see, for example, what's going on. And an important thing that I think is worth noting at this point is that we can drag in comments under miscellaneous, and we can say that this would be, say, the second excited state energy. Okay, and so this is a way to comment your code so that it doesn't end up looking like spaghetti. And I'm not doing a terribly good job with keeping things neat right now, but it is very straightforward, for example, to use a scope node to hide unnecessary details of a composer simulation. But I'm not going to get into that right now just for this tutorial. So that's great. What I want to show you now, though, is how to make a linear combination of states. So I'll just drag over here and delete this so that we don't clutter up our file any more than we need to. And I'll pull out this linear combination node. Okay, this is great. So I can wire it up here. And again, I can set the number of eigenstates however I like. You want this number here to be less than or equal to this number. Otherwise, you're not going to be able to calculate any of the higher order eigenstates here. And so that's just a minor detail, but an important one if you're trying to get things right. So what I can do is I can look at a position plot. This is a nice way to visualize a state. There are a couple of options that I have for visualizing a state. For example, I can put it here, and I can say that I want to see the state, and you see that, as expected, the state that I have here, which is just the ground state with the real part of the coefficient in front of it as 1, and the imaginary part of the coefficient in front of it as 0. You see here that the real part overlaps as it should. I can, for example, make this the second excited state by just changing the 1 to move it to the second row, and you see that it pops up here. I could make this purely imaginary if I wanted, and you see that the real part is now 0, but the imaginary part is going to overlap now with the state. And so that's really cool. I can even show the magnitude of the state. But of course, this graph tends to look a bit cluttered if I go there. So I can look at this position plot, and that makes things a little bit easier. And so I wire up the potential, and I wire up the state. You can visualize the potential, and now you can visualize the different aspects of the state. So let's just set this axis so that these things are much easier to see. You see that the real part of the state is 0. The imaginary part, as we said before, looks like the second eigenstate, and then the magnitude squared of the state looks as it should. It's basically the absolute value here. One thing that's really nice is that you can also see the expectation value of x and its variance, sigma x. And so this is shown by the expectation value here is this line in the middle, and then sigma x here is shown by these dotted lines. And so that's a really nice way that you can visualize what's going on. So this is pretty useful, and of course you can click on and off the plots as you wish. So that's cool. We can also set up a linear combination here. For example, I could start with an equal superposition in the ground and the first excited states, and I end up with a state that looks something like this. Because I have no imaginary part here, the imaginary part is 0, and then the real part looks like the linear sum of these two states here, as it should, and then, of course, we have the magnitude squared, as we should. So this is great, and this is a really nice start, and it's an excellent way to be able to visualize different systems. This can also be done for systems that are not easy to calculate. For example, I could change this to the anharmonic oscillator, and its composer calculates it right out without this being any problem. So this is a nice way to visualize things that are not necessarily easy to calculate on paper. So now I can show you how composer calculates expectation values quickly. So what I can do here is I have different operators and I have expectations. So let's do the position operator first, just to be sure, because this one we can check actually with the plot. We see now that it's actually off of 0 a little bit, which is pretty cool. So I hook up the spatial dimension because this is the x operator, and now I can hook up an expectation value node. So here I have x as an operator, but now I need a state to reference it to because you need to put a state inside of that integral, and you see here that as soon as I hook up my linear combination, the expectation value goes to 0.5. I can show you that this is working because if I make this only the ground state, now my expectation value is effectively 0. This is a very small number, and composer is looking at it as a fancy way of saying 0. This is, of course, because we're doing numerical quantum mechanics, and so we are not 100% accurate, and the errors are going to be due to numerics, which is the case for anything that's doing numerical quantum mechanics. So in that sense, composer is not special. It's doing its best. So let's go back to our superposition state. I can show you that this doesn't just do position, this does momentum. So I give it the spatial dimension node, and I can give you the expectation value, and we see actually that the momentum expectation of this state is 0. That's pretty interesting. We can look at the standard deviation, for example, of this state, and you see that we get something that looks suspiciously a lot like the square root of 2. And so this is interesting. These are ways that you can calculate expectation values and standard deviations. A note quickly on units. You can go to the website and understand a little bit more about the units behind what's going on. Basically, to make things easier to calculate, we've set h bar to 1, and we've also scaled other units so that we're not dividing or multiplying by excessively large or excessively small numbers, which is not a good thing to do if one is doing numerical quantum mechanics. So you can get details of that on our website. So this is pretty cool. Let's look at time evolution. So just to keep things from being too cluttered, I will delete some unnecessary plots here. And let's go looking for time evolution. Oh, this is nice. This says time evolution. Ah, very good. Okay. But we also need a for loop. And so basically, what's going to happen here is that this for loop is going to run our time from time t equals 0. Let's just name this t0, which makes things easier to see what's going on, to some time tf, which is the final time. And then I need some time resolution, dt. So we'll just run this from 0 to 5 with a time resolution of 0.05. Now, the finer your time resolution, of course, the slower things are going to run. And so it's typically a trade-off between how quickly you want things to run and then how accurate are your results going to be. So here we have our for loop that we've set up. I can drag my time evolution node into this. And so what the time evolution node wants is it wants our time resolution, dt, that we can drag into the scope. And you see that as we drag it into the scope, we get this edge node here. And let's just rename it dt. I tend to like to do this because it helps me understand what the different parts of my simulation are doing. I can even work here with the Hamiltonian here. This h of t does tell us that this Hamiltonian can be time dependent. Right now we'll just work with the time-independent Hamiltonian, but you can indeed set up time-dependent problems where your Hamiltonian varies in time. You can look at the control part of the reference section on the website for more details there. Okay, and then it wants an initial state. Well, as an initial state, let's use our linear combination. We know that that's not a stationary state. And again, let's just call it psi naught so that I know what's going on here. So what this is going to do is for each value of I, it's going to step forward in time by one step, and that time step is going to be determined by dt. And what it's going to spit out is a state psi of t. So let's move over here. I'm moving basically with the right mouse button. If I click the right mouse button and move around, I can move the simulation around. I can zoom in and out with the mouse wheel, so that's useful. Composer, I think, works best with the mouse. It can be done, though, with a laptop. Okay, so let's do a couple of things. First, let's set up a state comparison plot. This is nice because then we can compare our initial state to our final state. And we don't need to wire our potential. We could if we wanted to. But you see here that I've got, again, let's just go from, let's go from -1 to 1. And then you can see we have the magnitude squared of the states, and they'll overlap because I haven't started any sort of time evolution here. And so my initial state here I have with the green dotted line. Let's zoom in a little bit so it's a bit easier to see. And then my state after some time evolution I have here as my green dashed line. So everything is set up and ready to go. All I have to do is hit play. So this play button or start, you can also hit the space bar, and you see that the state evolves back and forth in time. Now, if I try to change a parameter, it says down here that we can't modify the graph while running loops. Have to press the reset button. That reset button exists up here, and I can click it, and you see that now everything is happy and we can work further. Just to give you an example of what goes on if you don't choose your time evolution properly, basically if I set dt to be too high, it just goes crazy. And so you have to make sure that your dt setting is low enough that the system can keep up. And this is just, again, a numerical issue. And so the easiest way to do this is just to test your time evolution on the system that you know. So this is really cool, but I want to show you one of my favorite ways to visualize this, and that's the state evolution plot here. So you can make the for loop a little bit bigger. This is great, but it needs a special kind of input. I can't just wire my psi of t here. Basically, I need to use this state aggregation node. And basically, this collects all of the different psis of t that happen for each of the different time steps and puts them all together in a list, which I could then visualize in this state evolution plot that plots the magnitude squared of the wave function as a function of time down here and then space up here. So I can press play again, and you see here that things are moving back and forth as they should. And that's really cool. So, yes, need to hit reset again. So this is pretty excellent. That's one of my favorite ways to visualize things. Now, I just want to show you one last plot, and that is the scalar time trace plot. And this plot's basically a scalar of your choosing over time. And so what it's asking for here is time, which is actually wired here at this I. And then it's asking for a certain type of scalar. Now, what type of scalar could we give it? Well, we can measure the fidelity, for example, over the overlap of the initial state with the final state. So, how does this go? Well, I have to wire in my initial state, and then I wire in my state at time t. Again, don't worry about the spaghetti. You can easily clean that up with some time. And so, just focus on what I'm doing here now. So, and then the fidelity here now comes out as a scalar, Let's just call it capital F so we know what it's plotting. And then fidelity runs from 0 to 1, so let's set our time trace. And now you see as I run that the fidelity oscillates, as it should, because we're oscillating back and forth between the two different states that make up our linear combination. And so in that, we'll go back periodically to the initial state that we started with. So this is just an overview of Composer, this very, very simple setup. And you can do a lot, and this can be shown in the various exercises that we have on the website. You can get more help with the reference. Just one final thing is that, of course, if you want to save, then, of course, you can save your flow file as you wish. And so it's this .flow. And so you save it wherever you want it to go. So that's just how you can save different things. It's pretty excellent. And so from here, I'll just bid you adieu, and thank you for listening to the Composer tutorial.